Okay, so yeah, can you guys hear me? Am I audible properly? Everything's good. Hello, hello. Someone let me know, please. Awesome. I'm gonna share my screen, and so the idea for today's session is that yesterday you might have been taught about what reverse engineering is and what we try to do in this aspect of cybersecurity. So today, what I'm going to do, I'm going to work through one problem with all of you, and so basically, there's a binary that I shared with you, and I'm going to disassemble that binary and show you how it's done. It is very similar to that problem that you were given in your SciSec app. How many of you had solved that problem? You had solved. So awesome. Okay, great, great, great. So can you guys let me know how you did it? Because I'm the one who made that question, so I just want to know. I don't think I took your interviews. Someone else did. So anyone interested in explaining their approach? Yeah, 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 yeah. How do you figure it out? It was SHA-256 and not something else. Like just guess or yeah, fair enough. So yeah, the objective of that was for you to analyze the questions, like analyze the binary properly, read some assembly and all. One similar question was there for the guild selections also. Like, did you guys take part in that? Yeah, so you'll remember there was one question that involved patching the binary essentially and bypassing the check. Yeah. So this one is very similar. The idea is this is something called a license checker. So a lot of programs have this because they only allow you to like use their privilege if you have a certain license. Let's say a gold member or a platinum member or something. And if you don't have that, then you cannot use that program, right? So the idea is there are methods by which you can bypass that check, and two of those methods are reverse engineering and patching. So I'm going to show you both. I'm going to show you how to reverse that, how to reverse some logic, or how to patch the logic, right? So I will start sharing my screen, and we'll go through that binary. Can you guys see my screen? I hope it's clear. Hello, hello. Yeah, awesome. So okay, hold on. Let's not. Okay, so this is my binary. It's called the license checker. This is the one I gave on the WhatsApp group as well. So how do you begin analysis? The first few steps that you must take is essentially figure out what the file type is, figure out what you can, whether there are some security checks involved or not. So one sec, someone wants to join. Yeah. So yeah, you start by figuring out what the binary type is. So for that, you can just use file or something. So if you do file, it'll tell you that it's an L64 bit and it's not stripped. You guys know what stripping and not stripping means, right? Or if you have any confusions, you can let me know. Okay, okay, one sec. I'll do it. So a stripped binary is essentially one in which the debugging symbols are removed. What debugging symbol means is, so for example, if I open this using GDB, and I'll show you what those functions are, right? So these are the functions that are present in this binary, and it's very clear by looking at it what the most important one is. It's this main function. So the reason they do this is because it makes in this scenario it makes debugging very easy. You just have to analyze the main function. All of these are basic libc imports. For example, this puts and strings and printf, all libc imports, right? And these are not important for us at all. So these are debugging symbols which are present in this binary. But if you see a normal binary that is in the wild, for example, any important program or something, then usually it will have its debugging symbols removed. So what that will look like is very different from this. For example, I'll show you. Might have a different binary somewhere. Okay, for example, MSF install, right? MSF Venom is is one attack tool basically. So it allows you to craft exploits. So MSF install is the installer for that. And if you check file on that, so it'll tell you that it's a shell script. Oh, okay, fuck. If it's a shell script, then you can open it also. So you can. It's not compiled essentially. So you can read the code and all of that. It's not important, but so for example, I've opened it and it'll tell you the entire code that it's running. But fine, because it's not compiled. I'll show you a compiled code that is stripped. You'll see the difference. A bunch of shit here. For example, record finder is not stripped. Okay, sad. What about Arduino IDE? Ah, look. So Arduino IDE's image is stripped. So if I do info functions here, you know what I mean. So yeah, see, when I do info functions here, it's a bunch of shit that is present here, right? And okay, in this case you can see the main function. In this case you can see the main function, but what happens when I try to put a breakpoint at main and run the program is essentially it'll start. Yup. And now when I disassemble it, okay, that's weird because it's essentially showing you everything, and it should not be stripped at all. I, fine. I hope you get what I mean. I mean, this was not the best example, and I wasn't planning to do this at all, so I sort of messed up. But essentially, a stripped binary is not supposed to give you any sort of information about what is present inside. So in this case, it's not stripped. In that case, also it was stripped, but it gave information. So I'm not sure what that was about. My cup, right? So, anyways, wait, did it clear? Did it clear what it? Uh, who was that guy? Manu Krishnan. Did you like get any sort of idea what I mean? I mean, the example was not clear. I know. I wasn't planning on this, so I didn't like really find a good one. But maybe it was an app image. So app images may have different criterias. But elf images, like these elf files, if usually they are not stripped, that means it's easy to debug. Otherwise, it's pretty much a nightmare. So, and you can set this flag while you are compiling it. So if you compile it using GCC or something, then there's a certain flag that you can use to strip the binary or not strip the binary. And by default, it strips it. So not strip just means it makes it easier for you to reverse engineer. So what do we do next is, again, I just showed you GDB, so I'm not going to do that. The first thing that you start doing after this, after figuring out, okay, it's an ELF file, it's not stripped, that means you can do something with it. Then you start with some reverse engineering tool. Let's say Ghidra, right? So I hope you all have used Ghidra before, or like, have you guys heard of Ghidra before? Okay, so Ghidra is a reverse engineering tool. It was developed by NSA, the National Security Agency, US. So I think it is open source now, so you can check out its repo also on GitHub. You can make contributions if you like. mean, it'll be pretty difficult because I think it's written in Rust or something, but we'll give it some time to open. So the idea is you open it with Hydra, and there's some decompilation that goes on. This must have been discussed in the last lecture also. So it will decompile the binary, and it will give us the raw assembly bytes, and it will give us a decompiled code, right? So what we then try to do is look at the decompiled code and figure out what it's trying to do, and see if we can somehow reverse the logic. So in this case, oh wait, I didn't even run the file. Fuck. So let me show you what the file actually does. So I'll run license checker, and it's gonna say that you don't use it like this, you use it like this. So you run it with some arguments next to it that has to be only numbers, right? So I'm gonna say okay, license checker. Let's say one sec. Let's say 30 to 23. So it's going to say wrong license code. So what I wanted it to eventually print is that you have bypassed the check. That is the right license code, even though my license. So the license code might be correct or not. If I want to figure out the right license code, I must reverse the binary. If I want to just patch the binary and say ki whatever I enter, just don't ever bother checking whether it's correct or not, then I have to patch the binary, right? So I'm going to show you both today. I'm going to show you how to reverse and patch. This is license checker. I'm going to open it using this dragon tool. So these are different tools that are here. The turtle one is a debugger, and this is one is the I think it's a trace. So there's something called L trace and S trace. So static tracing and some L tracing or something. So it's something related to that. But we're just going to use normal decompilers in this case. So I've opened it using this dragon tool, and it will start decompiling as soon as it opens. Right. So yeah, so the goal is to again either reverse it, so figure out the right code, or just patch it. That means whatever I say is correct, irrespective of like it should just never check at all, right? Okay. Yes, so I want to analyze this. It's gonna ask if I want to analyze it. I'll say these defaults are good enough. You will rarely ever require to click something here, so don't bother with that. You analyze it, and you can see the status bar down here. So it's disassembling the entry points, and it's figuring out the entry point essentially, which is the main function in this case. So as soon as this stops, that means your decompilation is done. It should be about now. So it's applying some function signatures and stacks, ASCII strings. Yep, and that's it. So this is how the interface looks like. I think this was discussed last lecture also. So the main points of focus for you guys is check out the functions first. If the binary is not stripped, then usually you'll have a bunch of functions here, and these functions might be interdependent. That is, the main function might be calling some other function. It's not there. It's not present. It's not like that in the present case because it's a very simple binary. But usually you can have some other function being mentioned here, like for example exit. In this case, exit is a libc function, but in other cases, exit or exit a, exit b might be some predefined function or user defined function, right? So you'll find all these functions here. The main interest for us is the main one, so I'll just click on main, and it decompiles in front of me here, right? So there are two things to notice here. There's this big window here, and this decompiled code, right? Now this is pretty much the C or C++ syntax, but this is the stack, right? This thing that you see here, this is essentially the variable stack. So what it's telling you is about 10 bytes into the stack is the local 10 variable, 14 bytes into the stack is local 14 variable. So you can figure out how big the local 14 variable is. That is 4 bytes, right? So it'll tell you that okay, 18 bytes below is a local 18 variable, so this is 4 bytes long as well, and all that. So it's just going to give you the variable sizes. It's going to tell how below it is on the stack, and this thing essentially tells you where the function's return pointer is. So the return pointer is about 8 bytes above the local 10 variable, which is how you can figure out where your return pointer is or where the function's variables are located exactly. So if you want to do a buffer overflow also, you can figure out okay, I should overflow the local 10 buffer, and then I should write about 8 bits to overflow the return pointer, and I'm done. things like that. Okay, so this is the assembly code for this same main function, and we'll come to that later. So let's first look at this one. So how do you begin analysis on this? The first thing that you should try and do is rename the variables, because local 10, local 18 is just very bad naming scheme, right? Are you guys following till now? Is it all clear? Okay, awesome. So the first thing that you try to do is rename the variables. So what? How do we go about that? Usually in binaries, when you see something like this, it means a stack canary. Okay, about 28, 20, 0x28. Whenever you see that, 28 bytes in FS offset, usually a stack canary. But in this case, canary is disabled. How do I know that? It's because the main function is never checking for a stack over or for a buffer overflow. Because usually if the canary is enabled, you'll see it reference the local 10 variable here again, and it's going to say, okay, if this check has failed, then you call the stack check fail function, and it will tell you, okay, I bypass the stack, and it won't let you execute code. You guys know how canaries work, right? Like, I think yeah, yeah. Awesome. So yeah, it's usually present here. So I know that stack canaries is not enabled, but they have still defined local 10, and you'll see that it's not referenced anywhere else in this code. So if I highlight local 10s, you see it's not present anywhere else in the code. That means maybe they tried to include it or something by hand. I'm not sure, but they never enabled canaries in this case. Then you see this if statement, right? What is this if statement? We already saw what this usage message was, right? When we try to run the binary without any parameters, it gave us this exact usage message, and it only prints if the param 1 is not equal to 2. So what this may potentially mean is that param 1 is probably what is checking how many arguments has been passed, and it is counting the function's name itself as an argument. So if I pass one argument, that is, if I pass dot slash license check with some number, then that means the number of arguments is 2. So param 1 is equal to 2, and it goes ahead, right? Only if it's not equal to 2 will it print this message. So now I can rename param1 as saying something like number of arguments, right? So how do you rename? You just go on a variable, you press L, like just press on L, it'll open the renaming page for you, right? Yeah. So if the number of arguments is not equal to 2, it prints this message, and it prints and it exits, right, with the status code 0. Fine. This is somewhere we don't want to be, because we want to essentially be here. If you look here, it's written premium access has been activated. This is what I want. But when I try to run this program with some random numbers, I get wrong license code. This is not what I want. So essentially, I want to be in this if statement. So I want my local 18, whatever variable this may be, to be 0x32. And what is 0x32 exactly? It is equal to 50, right? So I want my local 18 to be 50. So if you right click on any number or something, it will open this sort of page. And so you can click on whether you want the float representation, binary, or hexadecimal, whatever, or you can rename and commit here, make some this comments, something, something, right? So yeah, so local 18 is my target variable. So I'm just gonna say, okay, this is my target. This is what I want to be. This is what I want to modify essentially to be equal to 50. Okay, so what I see now is initially my target is set to 0, and there is some other variable that is also set to 0, and there's a while true loop here, right? So now what I'm doing right now is essentially reversing, trying to figure out the logic behind what ensures that the target variable is 50 or not, and then I want to see if I can come up with some sort of parameters such that my target variables becomes 50. That is reversing the code. So okay, it goes on to a while true loop, so it's going to execute indefinitely. And when does it stop? It stops if a certain variable is less than local 14, local 14 being 0, right? So I'll just say, okay, and this certain variable is the length of the second parameter. She's param2 and 1. So in this case, what param2 1 probably means is that the second argument that you pass along with the function's name. So function's name might be param2 comma 0 or param2 bracket 0, and param2 bracket 1 probably means the number that you're passing along with it. So it's going to typecast that to a character first, and then it's going to take the length of it. So if you can like understand C code, this is probably what's happening. So it's making a pointer, it's making a character, essentially casting it to a character, to a pointer, and then taking the length of the entire string. Uh, okay, if you double tap on a certain function, it takes you there. It's not what I want, so I'll just go back. Yeah, it's typecasting to a string and taking its length. So I'm just gonna rename this as length of input number, right? So it's gonna say, okay, if the integer length of the input number is less than local 14, what is local 14? 0. Okay, so my number has to be something. It cannot be negative, obviously. And if it's not, if I don't enter a number, I end up here. So what this actually means is I'm going to increment my local 14 maybe later in the code, and I'm going to keep checking whether the length is actually bigger than 14 or not. As soon as it gets bigger than this iterator, my code should break, right? So I'm just gonna call this an iterator. Okay, so if the length is less than the iterator, it's gonna break. Fine, awesome. Now what's happening here? This is the interesting part. So if you look at this properly, then what it's actually doing is it is basically taking um, it's basically casting it. It's basically taking every single number in your param2. So param2 comma 1 is the number that you enter. It's gonna cast this entire thing to a character, and it's going to make a pointer to that, right? So what that means is I'm essentially making a pointer to where the iterator is on the param2 comma 1. So if my param2 comma 1, say param2 slash bracket 1 is, let's say, 1 2 3 4 5, and initially my iterator is 0, then I'm going to say, okay, my iterator is 0 and it's 1 2 3 4 5. So I'm going to look at 0, and my pointer is going to be at this exact 0, right? The next time when I increase my iterator, I'm going to go here. My pointer is going to be here now. So essentially, it's a for loop going over uh, uh, each number in the each letter in the number that you enter, essentially, right? Do you get this part of the code? Like, if you don't understand, you can always Google how to read C code, or how to read this part of the, or any certain part of the code. But this is what it means. It's essentially incrementing the pointer to the param2 ka array, and saying ki, okay, you point here first, then you point here, then you point here, then you point here. So my local 19 holds a pointer to that essential number, into that letter inside the number. So if it's 111, so 1 2 3 4 5, then a local 19 can be either 1, or it can be 2 or 3 or 4 or 5, and it increments. And why do I know it increments? Because this is an increment code here, right? So what's essentially happening is local 19 will hold the variables. The local 19 variable will hold the number, individual numbers from the big number that I enter, and it's going to store that. So I'm just going to rename it as pointer to individual number, right? This is the pointer to the individual number. Did you guys get this part? I mean, I think it was not very clear to me initially, but if you're familiar with C code, I don't think it should be that big of an issue. Is it clear, or do you guys have any doubts? Awesome. Okay. So this is pointed to an individual number, right? Now what am I doing later? So this ATOI function, if you're getting familiar with C code, this basically means convert that string to a number. So far I had stored it as a character. Now I want to convert that to a number, right? So, and I'm using this reference here. So this is basically that individual number. So ATOI converts it back to a number, and what I do is I increment my target with that individual number. So what is happening in this code is basically whatever number I enter is going to go over each individual number in that big number, and it's going to keep on adding that to the target variable, which is initially 0. So basically, I'm taking the sum of the entire thing. So you can think of it as, if I enter 1 2 3 4 5, then what my target will eventually hold after all of this happens is 1 plus 2 plus 3 plus 4 plus 5. Because initially it was 0. In the first iteration, it's going to be 1, because that individual number becomes 1. And the iterator increments, right? Once iterator increments, I'm going to point to the next number in this param2 in the number list, and I'm going to convert that to a number, and I'm going to add that to target, so it becomes 1 plus 2. And with this check is still valid, so my length of input number, that is, let's say 1 2 3 4 5 is 5, but my iterator is 2, so this is still valid, it won't break. You continue until my iterator becomes 5, and when it's 5 it will still increment, so I get 1 plus 2 plus 3 plus 4 plus 5. As soon as my iterator becomes 6, it's going to break, and it's going to return the target variable, right? So then it's going to check if target is 50. So now we know what actually happens in this code. We have reversed it successfully. We have said here, okay, whatever number I enter is just gonna take the entire sum of its individual digits, and if that sum is equal to 50, it's gonna say, okay, premium license has been activated. So, so with that logic, if we try to crack this code now, if I say, okay, how can I get it to equal 50? I can say, okay, I will enter 10 fives or something. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. If I enter 10 fives, the total sum should be 50, and I should get premium access has been activated. Does that make sense? So technically, there are multiple ways you can crack this code, right? You can say, okay, I'll enter 9 5 times, I'll enter 5 once, it's gonna work. Or I'll enter 5 here and I'll enter 4 nines here, it's still gonna work. So there are multiple ways to crack this code. It's not very secure. Obviously, it's not secure, but yeah. So this is essentially what reversing means. You look at the code and you try to figure out what is happening, and you try to reverse the logic. Okay, if this happens, then how can I ensure that whatever my input variable is, it gives me the right answer. In most cases it won't be this straightforward. This is a very basic example. So, and in most cases you won't be able to understand the C code also, because it's not technically C code, it's very weird version of C. So I think it's called C90 or something. Anyways, so what you want to do then is convert the main logic into a language that you're comfortable with. For example, I like Python. So what I did when I first saw this thing is, I'm not very good at C code at all. So what I did is I went and converted this entire logic to Python. So there's this logic code that you see. Yeah, this is what I wrote. So I figured, okay, it's gonna check some code. It's gonna initialize some variable to 0. It's gonna take the length of the input. Fine. And then this while true loop comes into picture. So while is less than the length, you basically take the input strings that value, because this entire type conversion and this entire pointer scenario, it's not very easy to understand. So you try to translate all of this into some simpler language that you're familiar with, for in my case Python. So I just said, okay, just take that particular value from the input string, and then you get that character, convert it to an integer, and then increment this and increment this, right? You get the answer. So as I said, you can just check with 5555 it works, or things like that, right? So this is what reversing is, and if you have any questions, you can let me know now. Otherwise, we'll move to what patching is and how we can patch this binary. So, any doubts? Any questions? Hello. Okay, I'm gonna assume that you have no questions. So this was Ghidra, and it's not very easy to patch things in Ghidra, because I'm not very sure why, but I don't like to patch things in Ghidra. So what I rather do is I'm gonna close this. I'm gonna open a different software. It's called IDA. So I'm not sure if you've used IDA before. It is pretty popular, but uh, most people aren't familiar with it for some reason. So IDA is another disassembling software. It's very famous. It's very good, and the best feature about this is it ensures that it presents to you a graph-like structure. So I'll show you what I mean. So when I open this file using IDA, it's gonna say, okay, this is a ELF64-bit by file, and okay, all fine, all fine. Disassemble all opcodes. Yes. So okay, and it's much easier to read assembly code in this case. So this is what IDA's interface looks like. You have all these functions here that we also saw in Hydra. You have the main function here, some all these libc functions here. You can see it has multiple different things. You can see the imports that it's making. So it's a glibc imports that it's making, puts string length and printf and all that. can see the exports that it's making, which is just the main function and some start. All of these are not important. It's the main function and the underscore start. It's basically a starter to the main function, which is fine. Then yeah, these are some variable types that it's defining, and yeah, this is the main interface. It's the best part about IDA. So it clearly shows you how the code logic flows, and it makes it very easy to read assembly code as well. So what's happening here is the usual now I'm going to dive into some assembly code as well. So what's happening here is whenever you see things like these are essentially something that sets up the stack pointer or sets up the function's entry point, right? Any program's entry point is usually set by these initial opcodes. So some push, move, subtract, move, something like that, right? This again, this FH, this 28H, we saw 28 back there. It's an offset. Is usually used for stack canaries, but in this case it's not enabled. If it were, then you will see another logic code going saying, okay, you bypass the stack or something, right? It's gonna make a check here. So the important things for us to consider is the compare instructions or the test instructions and the jump instructions. The compare and jump, when you're patching, you want to essentially see compare and jump. So compare means you compare one register's value with another register's value, and jump means you essentially jump depending on whether the comparison result was in whose favor. So JZ means jump if true. So if the comparison result gave true, that is, if this were, let's say, in yeah, this were wait no, JZ means jump if equal. My bad. JZ means jump if equal. Jump if true is something else, I think. What was it? Wait, let me clarify it. Oh yeah. So JCC is this. No, I want in x86. My laptop's a bit slow because it's old. Um, okay, anyways, let's forget that. So JZ is either jump if true or jump if equal, one of these things. And yeah, what I wanted you to focus on is the jump instructions, compare instructions. And what this jump means, JMP, is essentially the best part because JMP is an unconditional jump. You might have seen right now also. So it means whether the result was true or false, I don't care. I want to jump. So it's usually called not after a compare instruction, but after some normal, as the normal part of the logic flow, right? So yeah. So why do you think this jump instruction is happening in the first place? Okay, this is jump if true. How do I know that? I know that because if you look at this very carefully, this is analogous to what was happening in that if statement that we saw in Ghidra, that was comparing how many parameters we have entered along with the function name, right? It's checking if the var24 value that is present in RBP is basically a stack pointer. If you increment the stack pointer by this value, if that value is equal to 2, it's comparing that. If they are equal, then it jumps where? Then it jumps to this part of the code. Okay. Yeah, then it jumps here. So if you see, it's a short jump, is what it means. The short means it's a short jump. That is, it's not the jump, the difference between the number of bytes is not much. Short jump to this function that is called LOC underscore 11C5. This is LOC underscore 11C5, and you continue the normal flow of execution. But if they are not equal, okay, so if the comparison resulted in a false, then it jumps here. So this red line that you see, it jumps here, and it's gonna say, okay, it's gonna start moving the the one sec. Where did it go? Sorry. Yeah, you can see the stack here as well. I'm gonna show that to you later. Like the same stack that we saw on Hydra, you can see that here as well. Yeah. So it's gonna give me this format thing. The format is a predefined character string or some string that is present in the dot data section of the binary. So it's gonna load that. So LEA basically means load effective address. It's gonna load the address of format here. Then it's gonna call the printf statement and it's going to exit. So exit usually acts on the EDI register, which is why you first move 0 to EDI and then call exit on 0. It's basically exit with 0, right? Makes sense. So you load the effective address of this format and you say, okay, your usage is wrong. you correct, please use it correctly, and then you exit. But if your jump was true, so if your jump resulted in the right thing, then you come here. And this is an unconditional jump, right? What is happening here, if you remember from the disassembly code, that this is basically saying I'm defining two variables and I'm initializing them to be 0. Move basically means you move this, the second value to the first register or the first stack pointer, whatever. So I'm moving 0 to variable 10, variable c that is present in this certain on certain offsets from the RBP. Okay, and then I'm going to do an unconditional jump here. So irrespective of whatever happens here, I'm always going to end up here, right? So now what happens here, if you can see, very, there's a very clear distinction, and this entire thing is in a loop, right? These two code blocks. So you can see that it clearly references this back. So it's going to say, okay, I'm going to move certain values here. I'm going to add 8 to the to RAX. Then I'm going to move, I'm going to do some shifting and all. I'm going to call string length. Okay, I'm going to call string length. I'm going to call string length on what? On RAX, or sorry, on RDI, right? And then I'm going to compare the values of var c. Var c was defined here, which is initially 0. I'm going to compare that to EAX, and then if the jump resulted in the, yeah, JL basically means what? JL means if the jump is false. So if the comparison is false, right? The comparison is false, I end up here, and then I come back to this loop. So if I end up here, what happens is, again I make some initial movements in some shit, and I basically increment 1 here to var c, which was just incrementing to the iterator, and then to var 10 I add ex. Ex held the value. In this case, it holds the value of the individual digit from the number. Right? It's not very obvious from this at all, and I don't mind if you don't understand what this is. Even I don't understand to some extent exactly what is happening. But I can see references to ATOI, which is something I saw before. I can see references to addition of var10 to certain numbers or incrementing of c. So I can understand what is, like, at some superficial level I can understand what's happening, right? So and then it increments and it comes back here. So this loop continues as long as this jump condition is false, right? So what happens if the jump condition becomes true? So JL is jump if false, jumps if false to this function header, which is here, right? So if jump, so it only jumps if it's false. So if the comparison results in a true, that means these two are indeed equal. Then in this case we end up here, right? So JNZ again means jump if not true or jump if not equal. So what happens is, I'm going to now compare that to this guy, to 32H. Now 0x32, if you remember, 0x32 was basically 50 to 32H. Now the H in the end stands for hexadecimal, by the way. So 32H basically means 32 in hexadecimal, which is 50. So I'm going to compare the value of var10 present in some place in the stack pointer, to which I was continually adding EAX. I'm going to compare that to 50, and then I'm going to say, okay, if that result was false, then I will jump to make a short jump to LOC underscore 1238, which is here. Okay, if that result was false, I'll jump here, which is essentially gonna say wrong license code. Okay, this is not what I want. What I want is for the comparison to be true, or I want this jump statement to essentially jump to this place, right? Jump here. So how do I patch this? How do I patch this is, I'm gonna say, okay, irrespective of what happens, whether what happens to this comparison, I want you to go here first, right? So in order to see that very clearly, I'm going to start one sec. I'm going to put this in text view, and this is where we are. Right. Now this is the linear flow. Now programs are executed in this specific order, right? This is why I started this mode of viewing it now, because what I want to clarify is, so this is the compare instruction, which is saying, okay, compare the EX register value to the var c, to the this essentially this value, and if they are equal, then I don't make this jump, and if they are not equal, then I do make this jump. And if I make this jump, I'm going to end up essentially where? Here, right? Oh, sorry, my bad. This compare instruction and this jump. So I'm going to compare that to 50. I'm going to compare that to 50, whatever value. And if that is not true, I'm going to jump to this instruction, this function, and this function is defined here. Is going to say wrong license code. That's not what I want. What I want is if I just never jump, what is going to happen is after this compare instruction, it's going to load the effective address of premium access as access has been activated. It's going to call puts on that. It's going to exit. So basically, if I somehow patch this to never jump, irrespective of what the compare instruction was, then according to the linear flow of the program, what I'm going to have is, irrespective of whatever value I enter, it's always going to load the effective address of premium access has been activated. It's going to always print that. So what I want to do is I want to patch this, right? So how do I patch it? I go to edit, I go to patch program, I go to change byte, right? This is the entire byte sequence for this entire instruction. What is this instruction? The instruction is jump if not true, to short. Short is also represented by some bits here. So some bits in this hexadecimal thing. To this loc underscore 1238, which is another function pointer, which is represented by one of the last few bits, right? So the first two bytes or the first 3 bytes are usually what the opcode is. I'm saying usually because it depends on how big or what your instruction is. So in this case, for jump, it's not true. As far as I think, it is 79, 75, and 19. The 75 and 19 probably stand for jump if not true. And I know that I can change this to no operation. You know what no operation means? No operation basically means if you hit that part of the assembly, just ignore it, continue further. So what I want to try and do is, instead of saying jump if not true, I'm going to replace that by saying no operation. So as soon as it compares, and then it goes to the next line, it's gonna see no operation. It's gonna say okay, fine. I don't have to do anything here. It's gonna load the effective address. It's gonna continue there, and it will never go to saying your premium that your license code is wrong, right? So I'm gonna try and change that. So the no operation opcode is 90, right? If you write 9090 twice, like 2 bytes, no up is basically 2 bytes of code, and it stands for, and it's 9090. So if I write 9090 here, what trying to say is, I'm trying to say, okay, from 75 to 19, that is jump if not true, convert that to 9090. So if you do that, all of this is just goes to waste. This it just does not matter. Okay. So as soon as you do okay, you'll see that it becomes no op. The two instructions that were further. So uh, y- why two and why not one? Because I just changed one. It's because if you change 2 bytes, then you're changing essentially two places in the assembly code. You can think of it like if I change the entire string to 1990, to 1990 that way, then the end your entire code up to, let's say, how many bytes that was. Um, one sec. I think it was 16 bytes or something. Then the next 16 bytes of code all becomes no up, no up, no up. It's probably 16. Yep. So the next 16 bytes of code just becomes no. If I change all of this to 90, that's not what I want. And you can see how this 90 actually plays into picture. Because if I go to a one code above it, and I try to patch that, you're gonna see 9090 come up here as well. Look, this 9090. You know that this 9090 is for the no op. So the compare instruction probably got over here. Okay, did someone? Okay, yeah. You please go ahead. You have any questions? Yeah, you can change the compare to an NOP. Essentially, you can change whatever the hell you want to NOP. And if you change the compare to NOP, you'll have, see, I can change these bits also. So we identify that these bits are probably compare, right? Because I'm on the compare line of code, and I have tried to patch that, and I know that these 1990 is what I just set. So all of this must be the compare code. I can change all of that to 1990, and this entire line of reasoning just goes to waste, right? So as soon as my program comes here, what? There's no, the flag never comes into picture now because the compare instruction is not present. So compare only changes a flag if once it's executed, right? So this compare instruction will set some flag, and based on that, this some instruction will happen. But because I'm not setting any flags now, it's just gonna say no up, no up, no up, no up, fine. It's just gonna say okay, this is next instruction I have to do. So I'm going to load this address to RAX and I'm going to start printing it. That's what's going to happen. Does that make sense? Okay. So like you can do this also. You can change the compare instructions, but um, that's fine. We'll do that. So I've changed the compare instructions. Everything is no op now. So what's gonna happen is it's gonna keep. This is a loop basically. If you remember, look, you can see here also. So this is looping back to this part of the code, and it's gonna keep looping, keep looping, keep looping, right? So if I now if I now yeah, now I've patched the binary essentially. I have changed some opcodes. Now I want to execute this. So why is this useful at all? I'll show you how to execute this later, but why is this useful at all? Is because in this case it's just printing some string, right? It's just saying premium access have been activated. But in like if you have heard of cracked softwares like let's say Minecraft or things like ANSYS or something, some big actual software that use license checking, the way people bypass these checks, the way you have cracked softwares is essentially through these things. It's because they patch the software, they look at the assembly code, they see, okay, this is where the main instruction happens. This is where it goes to some, let's say, it makes a call to some web page or some web server, and it fetches your information from there. It checks whether you're a valid user or not. And when you bypass that check, whether you're a valid user, it does not matter what you did before that. When you bypass that check, you essentially have access to the entire software because of the linear structure of how the flow has been, of how the flow is, right? So, in fact, if you have you guys heard of Pravartak Technologies? There's this ITM startup in Research Park. So they had released a hackathon a few months ago, I think, and their problem statement was what they want is not a linear flow of instructions in the assembly code. They wanted to branch out. So if an attacker, let's say, uh, bypasses certain if an attacker patches some binaries, or if an attacker patches some codes, then you want to branch that. So you don't want to hit that code at all. So there was this weird PS. It was very difficult. I tried to do it, but it was very hard. So yeah. Anyways, so yeah, I've passed the binary. Now I'm going to save that. So I can save it using apply patches to input file. So it's going to say, okay, I'm going to apply patches to license checker 3. I don't want to create backup. I don't want to restore original bytes. I'm just going to do okay. So you'll see that here it has applied 6 patches. Why 6? Because these are 6 in number, 1, 2, 3, 4, 5, 6. 6 patches have been applied. So now if I go to my binary, one sec, it's gonna load, like it's gonna initialize my ZSH file. Yep. So now if I load my binary, if I run this binary and I'm gonna say run random number, it's gonna say premium access has been activated, irrespective of whatever number I enter, right? So I can enter 1, 2, 3. I can enter just 3. It's gonna say fine. Earlier it was checking whether the sum was 50, but now it's not because we have passed the entire binary. We have said key, okay, all of these instructions are no op. It does not matter whether you check or not. It does not matter what this value is. Always print this, right? So this is the idea of patching. So if you have some free time, you can go through some more uh, advanced binaries. There's this website called crackme's.one. I think I've shared this link with you all before also. So even I've uploaded some binaries here of my own for other people to practice. So you can check latest crackme's here, and there are a bunch of different things you can try. All of these are various difficulty levels. This is 4, this is 2.4, all of that. So essentially, just pick a binary, try seeing if you can patch it or if you can reverse it. Reversing is usually harder because if figuring out the logic is tough in most cases. So there was this question that I made for the reverse engineering CTF. It involved Huffman coding. So in order to figure out that it is Huffman coding through the decompiled code, it was very difficult. So in general, it's hard to reverse. It's very easy to patch. But if you have stripped binaries, if you have binaries where you can't see the debugging symbols, or there are some binaries in which there's anti-debugging tools enabled. So there's something called the int3 instruction. I'm not sure if you've heard of it, but whenever you debug something using, let's say, GDB or something, then the way it works, then the way you and when you set breakpoints, the way breakpoints work is they modify the code internally, and so that whenever the compiler hits that certain part of the code, It's gonna say, okay, I've hit that part of the code. This is my debugger's code, so I'm gonna execute the debugger's bits. So that's how the debugging statements get executed. So yeah, so there are some programs which are anti-debugging, so they don't let you put that break statement. So as soon as you try to put that break statement, they're gonna say, okay, I won't let you debug, things like that. So there are a lot of security mechanisms around this, and most programs are secure, but they cannot prevent themselves from being open through a disassembler, because the process of decompiling it is very easy. You just have to look at the machine code and translate that using predefined libraries or predefined ideas of how exactly machine code translates to a normal assembly code, and you just make that translation. There's nothing that can stop you from looking at assembly codes. So if you can learn to read assembly, then there's nothing that stops you from reversing a program or patching a program. So that's how the best uh, reverse engineering people are, I think. Yes. So there's this another case of reverse engineering. If you've heard of WannaCry virus, was this told to you before? Yeah, 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 yeah. So he figured out a kill switch through reverse engineering the virus or something. So it's pretty cool. Like a lot of softwares like Minecraft and all depend on this, because otherwise no one would have the free versions of Minecraft. Like they're not dumb enough to release a free version with a licensed version, right? Same goes for Ansys or any 3D, it's like SolidWorks or some other analysis platforms, or LT Spice, I think. Yeah, probably, or Altium, some PCB designing softwares. A lot of softwares are cracked because of this reason. So I hope you enjoyed the session. That is it from my side. You guys have any questions? You can ask. Any questions? Yeah, a lot of them are Windows binaries. I didn't see this message. Yeah, but then there are some Linux binaries also. For example, you can filter the search here. Besides, Windows binaries are much more fun. It's because sometimes Windows Defender itself does not allow you to download that, so you have to disable the Windows Defender first, and it gives you a whole new feel for how of a reverse engineer, like full reverse engineer sort of looks. So yeah, these are all Windows, I think. So these are all Unix, Linux. Yeah, these are all Linux binaries. You can check any of these, or you can check Windows binaries if you want. Then there are different programs that they are written in. So there's C, C++, there's Java, there's Visual Basic. So if you want to practice some, like they say, .NET programming, then you can try that also. I won't recommend it because it's very difficult, but sure, why not? Different architectures. So there's ARM, there's x86, there's Java architecture, there's MIPS, all these things. So it has all sort of flavors. You can try them. Change difficulties if you like. So yep. Any questions? Okay, assuming none, I'm going to then end this meeting. So, okay, bye bye then. Hope you guys had fun. See you later.